Introduce you to Chen, who is from Taiwan. He's a numerical analyst, and he's also the chair for PyCon Taiwan this year, right? Yeah. The first time that they had PyCon Taiwan, and some of us from PyCon JP also went to Taiwan and met up with them to join PyCon Taiwan. So they came over here to present and also join PyCon JP this year. So without much further ado, I'll pass on to Chen for his talk.
Hello. Yes, thank you very much for staying in this room for this quite remote topic for this conference. Yeah, what I'm doing is to solve partial differential equations. And in general, I am a computational scientist. And my interest is in dealing with some physics, in macroscopic physics. And I want to model that in the first principle way to directly solve the governing equations of these physical processes. And I use Python in the past several years to construct the software that I'm using. And in our setting, actually, what we needed to do it in a massive parallel fashion. And we found that Python is very important for our productivity. So I put this slide online, so if you want, you can check it, because there will be quite some some information about physics. So today, my talk will be in 3 parts. At the beginning, I'm going to introduce the background of all this scientific research setting. And then I'm going to introduce the design of the software and why and how we use Python and how the software is structured. And at the end, I'm going to show you some simple example by how to use this library to do numerical simulation. Okay. So what I want to do, so maybe conservation laws is quite remote to you, but if I say this is something that governs the world, it will make more sense to you. So when you see, okay, this thing is a supersonic flow past the bullet shape thing, and you can see this not ordinary waves, they are shock waves. So if you are bypassing a shock wave, you will be shocked and shattered into pieces. So it's a very strong and violent physical phenomena, and you will see that when you are designing missile or supersonic vehicles, and of course satellite and rocket into spaces. And we'll see something like a typhoon, which is coming toward Japan, a strong one, and it's a highly nonlinear phenomena that basically you cannot analyze it, and but we really want to know about it because it causes a lot of damage into our society. And this is seismic waves inside our Earth. Okay, this is what people, seismologists, do for global seismic wave patterns. And this is electromagnetic wave. All these things are governed by conservation laws. In general, they are just, conservation of mass, which you learn from elementary school, conservation of momentum, conservation of energy, conservation of angular momentum, things like that. There are only a handful of conservation laws, and we formulate these theories by using this fundamental concept into mathematics language. Okay, so what we want to do is we want to know more about it, but I think the most solid way is to do experiment. The problem is that experiments are expensive. This is a facility for hypersonic flows, which is, I think, is located in NASA Langley Research Center. You know, this is large. All these tanks are filling with gas. I don't really know how it's working, but what I know is that if you run one test of it, it will cost a fortune. And sometimes we don't want to do experiment, or we can't do experiment, right? And even if we can generate a typhoon, I don't think anybody will allow you to do that. So like what we worry about with LHC, right? So what we want is we want to model this thing in computers. And in computers, because we know few about this phenomena, so we have to resort to the most fundamental theories, which is conservation laws. And we formulate them into mathematics formula. And of course, it's a very gross description of it. But in general, it can accommodate all these different phenomena. And we call this partial differential equations. And this is the integral form of the partial differential equation. So when we have the theory, which has around decades of research, then it becomes a problem of programmers. How do we solve this equation? First, we need to come up with some good numerical algorithms, which live in the discretized space of, in general, we cast this into some difference equation so that we can try to solve it in computer. But then, still, we need to try to create this difference in things into computer codes. So we need to have some ways to discretize the space into smaller pieces we call elements or cells, and to have an appropriate data structure to host them. And the problems are usually very large, so we need not only one computer, but aggregation of computers, usually thousands of nodes or tens or hundreds of thousands of nodes. And then the problem will become, we have on hand is how to analyze the data we calculated. Okay, so another question, because it's a programming problem. So as we know, as a matter of fact, Fred Brooks told me that if you can buy something from the shelf, you should buy it, right? It will deliver you more productivity. So it's not a really technical approach. So if we have a lot of commercial codes on hand, why not use them? The first answer is that they have a business and they have to protect their IP, and they don't want to show us the source code. And as a scientist, if I cannot see the source code, I don't trust the result it generates. And second, when something can be commercialized, it means it has a larger pool of users, and which also implies that this technology is more well verified. But if we were doing cutting-edge research, we don't have the luxury to have some well-verified thing. We are verifying things. And the code we want to use sometimes, usually doesn't really appear in commercial area. So we either have to write our own code, or we have to modify or make extension of these existing codes. So if we have some good open source code, it will be great, because we have the source, and we have the right to modify it, and we can obtain the result more quickly. But for my problem, the existing good open source code doesn't really fit my needs, so I cannot use them, although they are pretty good. And of course, there are a large pool of research code available, but most of them are written by graduate students. And not all graduate students are good coders. So you know what it means. Sometimes, it's a real story that I have about 4 or 5 versions of code in my previous research group. So they are one code actually, but they cannot interoperate because everyone needs to graduate, right? So then the code becomes quite unmaintainable. And actually, I learned some secret recipe of numerical algorithm, which is very good at dealing with the conservation laws. And nobody has implemented into maintainable function. So I want to do it. And it's called the conservation element and solution element method. It's very amazing that it can direct solve the equation that I show here, which is quite outstanding trait of numerical algorithm. And I've really done different physics with SOLVCON and all this numerical method. So now, I can define SOLVCON right now. It is a Python-based software framework that can construct time-accurate solvers for conservation laws for virtually any physical processes that can be described by conservation laws. And currently, I have two referential implementation of solvers in the by using the CES method in SOLVCON. And we use unstructured mesh of mixed elements so that we can model arbitrary geometries. And we use MPI, which is built in SOLVCON to do parallel programming. And my goal to SOLVCON is I hope I can come up with a toolkit that can be incorporated into other applications to solve a more general problem or to be used like some commodity thing. Okay. Here is some application of SOLVCON. This is we call stress waves in solid. In general, if you hit something, there's some wave inside, so we can hear something, right? But in this solid, is the waveform is it's stress wave, which means the stress is oscillating. It's not in air, it's pressure oscillating, right? But in solid, it's stress oscillating. And in stress, because solids is quite complex. In fact, I think most of solids actually is anisotropic, which means the property along different direction will differ. So you will see this wave when you throw a stone into the pond, you will see circular waves. But in anisotropic solid, you don't see circular thing. So you can see this cusp in the circle, and it's actually not circle. It's some strange shape. This solid, this barrel is of hexagonal symmetry, so you can see some symmetry thing. There are also solids which we call triclinic. There's no symmetry in this crystal structure. And our simulation code can do exactly what described by the equation. And we do, well, actually my actual background is computational fluid dynamics and supersonic flows. And we've done a lot of verification of SOLVCON for supersonic flows. There's some examples. There's a flow past a cylinder. There's a shock wave past a dust layer, so that you can see a lot of reflection and refraction of shock waves. And there's an oblique shock wave hitting a reflection of oblique shock wave. And there's many of them that I cannot show here. And the most interesting thing I've done so far is the problem we call supersonic jagging, supersonic crossflow. Here we have a hole that we feed some supersonic air into this spatial domain. Then we have another supersonic flow flowing from left to right. So that you know if you put something inside a supersonic flow, you will have a very violent interaction between them. So that you will see this is a bow shock we call, and there's a secondary bow shock, and this is a barrel shock, and there's a what we call Mach disk, and all this in the complex vortex thing happen behind that. Why we want to do it is it's very important to do a hypersonic engine. Because that's a whole story behind it. I'm not going to say here, but it's a very sexy problem, and you need a big computer to accommodate 66 million elements. And trust me, it's not large enough. It's just a moderate size for you to see some of these effects. So physically, that's what I done. And in terms of runtime performance. All these tests I've done at Ohio Supercomputer Center, where I was studying at Ohio State. And I have tested up to 1,000 cores of this code, and by using different sizes of the mesh. Why do we care about high-performance computing? I cannot say it's supercomputing, because for supercomputers, you have to utilize up to 100,000 cores. Okay, so this size is still, well, like a kit. But the scaling is very promising. It's not perfect, but as I increase the size of element used in the simulation, which I say there's a problem size, I can have a pretty decent scaling rate to the ideal scaling. So when I keep increasing the number of computing nodes or computing cores, I can still get speed up. And you know that when we are doing parallel parallel computing, there will be some communication between different nodes. So there always overhead. So the issue here is how to control the overhead, so we can still have the speed up. Okay, here is the second part. I'd like to show some internal design of SOLVCON, which is how I do this in Python. We use, well, in general, we have to discretize the spatial domain, as I said. And there are many ways to do it. For example, a simpler way to do it is to do the structured way. So we think this is a three-dimensional space, and we cut it in 3 dimensions. And you got a lot of cube in the space. Each is an element. And you apply your numerical algorithm in each of the elements. And they are regular, they are well-defined, and you know exactly what is behind and to the left, to the bottom, to the up of your element. But this poses a large limit into the shape you want to model. You cannot really model a rabbit by using this regular mesh. So what we want is we use the unstructured mesh, and we design data structure to accommodate this mesh and let numerical algorithm can operate on them. And we are not only do unstructured mesh, we do unstructured mesh of mixed element, which means in this mesh, it's not only triangle. It can be triangle and quadrilateral in 2 dimensions. In 3 dimensions, it can be the mixture of these 4. So that something adjacent to you may not be something like you. And we have the data structure to accommodate this. This is what we do. Okay, take this tetrahedron, for example. We know the nodes for this cell on here, and we know the faces for the cell. They have it has 4 nodes and 4 cells, 4 faces. And what we need at first, we need the global index for nodes. We need to know how many nodes we have. And they define the geometry of the mesh we need to use. Then we need to know the connectivity among these elements we call cell, because we use cell-based solver that we store this value in the cell center. So we need to know the nodes in each cell. We need to know the faces that become the boundary of the cell. And we need to know for each face, it's composed by which nodes. And we want to know, for conveniency, we want to know the cells connected by one face. In our current data structure, we allowed only 2 faces be connected by 2 cells be connected by 1 face. But it's not necessarily in this way. We can, in the future, maybe we can extend it to allow hanging nodes. But that will make life much harder. So with that data structure, data structure itself cannot become algorithm. We still need algorithm. And for all PDE solvers, we always have 2 levels of loops. And we have to have loops. No way to do recursion. We have to have loops. And the general structure is always we do initialization. And we have an outer temporal loop which do time marching, we say in time accuracy solvers, or pseudo time marching if there's no time in % of the solver. And within the temporal loop, we have a lot of one or many spatial loops which iterate over the discretized spatial element and to perform the numerical algorithms. And if some termination condition is met, then we finalize the solver. This is general structure, so it's pretty simple. What makes it complex is if you bring input and output, if you bring parallel computing, if you bring the analysis and the visualization all inside this structure. That will be complex. But in general, the fundamental workflow is this. And we do in SOLVCON is to materialize these 2 loops. We first do from the inner one. We do the inner spatial loop, which actually is where we implement numerical algorithm, because numerical algorithm need to operate in for every discrete spatial element. In SOLVCON, this thing we call solver kernel, and it is actually a Python class. And we have a base solver implementing SOLVCON that provides some facilities to be used for many things. But it doesn't really implement the numerical algorithm. And we need to have a concrete solver to subclass the base solver to provide the hypermesh code that we need to use in the numerical algorithm. And usually it's in C, but you can, of course, do that in Fortran, anything you like. Ruby, yes, you can. And anything. And for multiple numerical algorithms or multiple physics processes, we can also use this structure of this class hierarchy just by subclass, and you can have different things. This is what we did for the different physics in SOLVCON. And higher than the spatial loops. Here we need to implement the temporal loop. And we put the temporal loop into another class hierarchy called case because it is essentially the control flow for a simulation case. And in addition to that, we have two other structures called hook and anchor, which are used to augment the basic flow so that we can put more logic in addition to numerical algorithms, so that we can do some post-processing or in situ processing, or do some on-the-fly analysis with this within this structure. So with the fundamental concept of two-loop structure, we can formulate the whole architecture of SOLVCON. So you can see this two-loop structure here, and there are some fundamental facilities for meshing, for distributed parallel computing, shared memory parallel computing, and some utilities, and have some application layer. And at the upper layer is how we control all these facilities. Okay, the third point of SOLVCON is to realize convenient parallel computing. In the setting of solving partial differential equations, we have two approaches. The first is to use shared memory parallel computing. The second is distributed shared memory parallel computing, SMPC or DMPC. Sorry, this is supposed to be SNPC. So the main difference is very simple. It's just difference in how you address memory. In shared memory parallel computing, all the processors can access the same block of memory. In DMPC, all the memory is distributed, so you have to do message passing. You cannot directly address it then. And you combine these two together, it becomes hybrid parallel computing, which will make life very interesting. In general, DMPC is much more complex than SMPC because you have distributed computing here. And but what we really need is DMPC. It's how we scale up. And unfortunately, we cannot use MapReduce because when solving PDEs, we have a lot of communication. You cannot block them. And thanks to the two-loop structure, we can easily by using the solver class to materialize shared memory parallel computing. So you just make some modification to your solver kernel, and you can run multi-core on your workstation. So what really matters is the DMPC. So for DMPC, we have this distributed memory, and we need to decompose again our already discretized spatial mesh, so that on each subnode, on each node, we can still use the same numerical algorithm as we have used for sequential code. But among them, we have to do the communication between or among these subdomains so that they interchange messages while we are doing calculation. And in order to realize that, say if this is our overall mesh, we know the connectivity so that we can build a graph based on this connectivity. Then we partition the graph. After partitioning, we use the partition graph to rebuild the decomposed subdomains and distribute it into different computing nodes. And when distributing, we are distributing, well, up to 100 to hundreds of thousands nodes. And we use MPI to do that. In general, we rarely use other technique because MPI is the fastest technology. And this DNPC can be very complex to implement and very difficult to be debugged. So what we have done is we have absorbed this logic into SOLVCON. So that when you write or when you implement your numerical algorithm, you don't dealing with that. You are dealing with your numerical algorithm, created it like a sequential code. And by following some rules, this sequential implementation can be just turned into DNPC code. So that this RPC and communication all happen in logic that's predefined in SOLVCON. So numerical algorithm developers shouldn't really need to worry about it. So after we have the parallel processing, parallel computing, right now we need to dealing with the problem with big data. So why we say this big data? Because for time accurate solutions, what we are looking at is quite large data set. So I've done up to 66 million. So it's a modest large enough problem. So if we have a problem of 50 million element and we have to run it for 10,000 time step and we want all the results for every time step, we will have 80 terabyte of data on disk, which is not very easy to be analyzed. So in the past, everybody are taking this workaround. We cannot output everything. So we are reducing the temporal resolution so that we still get a large but treatable size of data. But still, it takes very long. The reason is that when we are doing calculation, we spend a lot of time to write the computing code, and we implement the numerical algorithm to make it very fast. But it is not the case for post-processing code. Post-processing code usually is not in parallel. They are sequential. And usually it's not multi-threaded. It runs on one core. So if you want to process 160 gigabytes of data on one core, there's a real story which I've been told by a researcher in NASA. He has a problem about 20 to 30 million elements, and it took him half an year to finish some result that can be published. And I think, if I remember correctly, the calculation only took him 1 or 2 months. All the rest are spent in post-processing. We need to deal with this issue. So what we do in SOLVCON is we do two things. The one technique we take is parallel. We just output all this data in parallel so that the output part will not take too much time. But still, post-processing is an issue. So we do in-situ visualization. We visualize, or we do this analysis right after we calculate the result in memory, so that we don't really need to output this data into disk. And we don't need another standalone application to do the analysis for us. There are pros and cons. By doing this, we run very fast, but we are sacrificing the memory of our simulation. So when you want to do that want to extract some more information, you have to run the whole simulation again. But it's not really a very big problem because the overall turnaround time has reduced from months to days. So you can do a lot of simulations and get the result while simulation has done. So in general, these two techniques has to work together because sometimes you still need some overall output so that you can see in detail. Because for simulation, you don't really know what you want to see before you get the result. So you still want some large amount of data for some snapshots. But for the rest, you can just do something in situ thing. So you see something you predefined, and you get the result. You have a picture about what this simulation is about. So this thing should be worked together. Okay. So here I'd like to show some example. in SOLVCON, I don't really have input file as many other code. And of course, I don't have a GUI. And what I do is I just use Python to drive everything. Like a lot of Python projects does that. And a driving script is the equivalence of input file for SOLVCON, but it needs to do the initialization and to start the running and to clean up things for the whole simulation. And but it's very convenient because it's a Python script, so you can do anything in the script. In fact, I've designed SOLVCON so that you can replace anything higher than the foundation layer. So anything here can be replaced in your driving script. So it makes testing very easy, and you can do a lot of things, and you can do a lot of parameterized study by using this structure. Okay. The problem I'd like to show is a very standard test case in gas dynamics, which we call SAS chart tube. And it actually is a one-dimensional problem, but I run it with a three-dimensional solver. And the code example is in SOLVCON, but you need a tool called Qubit to generate the mesh on the fly. Yeah, the generator is already in the script. So let me show you something. Okay, this is where I put the example. And you just hit go, and it will compute, hopefully. Yeah, the mesh is generated, and it's begin computing. As you can see that, yeah, it's in multi-threaded mode, so CPU utilization is about 200%. It will take quite a while. That's still, yeah, about 5 minutes, well, 3 to 4 minutes to finish. So I have pre-computed the result here, and we can see the output file here. Okay, this is a, let me do it from the beginning. This is the initial condition of this problem. So you have two regions of gas. And this region you have a higher density and pressure, and this region you have lower density and pressure. And initially you have a diaphragm between them. And it's something can be experimented. So gas dynamics usually use this problem to characterize some gas and characterize some combustion. And when we start, we remove the diaphragm so that you will see something happen, right? And what really happened is that, okay, let me do it this way. Let me cut this domain so that I can see it more clear. Okay. Okay, this blurred thing is because of interpolation. The front edge is what we call shock wave. And there's another discontinuity here we call contact discontinuity. And there's some blurred range of change is the expansion wave. So that all interesting phenomena of gas dynamics, nonlinearity of gas dynamics happen in this problem. Okay, so it's just pass and pass the domain of calculation. Yeah, this is the driving script we've written, and I can explain more about this, how to write this driving script. Okay, in general, there will be 3 parts of this thing, because for any problem, numerical algorithm in general doesn't need to know anything about initial condition nor boundary condition. They don't know. So we have to tell the algorithm how to set the condition of this problem, right? In addition to the geometry of the problem. So this part is where we put the initialized anchor. and to tell the simulation to do the initialization. And here is how we construct other parameters in the simulation. And finally, we need to run it. And this is the anchor that will be associated with the solver. And it is a callback method that will be called when we initialize this simulation case. So it will just set some variable and fill the necessary solution arrays that's used in this calculation. And second part, we have to specify other bookkeeping things and to tell the system what we want to see, what we want to output, and how we want to do initialization. Actually, there are some predefined initializer in SOLVCON that you can use. But for this special case, we don't have something ready. So we wrote a custom initializer here, right in the driving script. Okay, finally, we run the case. And this initializer callback anchor is being called in this initialization. So there's a lazy evaluation. When you construct this case object, you don't really do something with it. What has been done is when you initialize it. The reason we do this is for parallel computing. Consider if you initialize something on your head node, then you don't really do parallel computing, right? So you have to do something after you have distributed or command all your work node or your compute node to prepare some facility. Then you initialize your solver. So you have to do some lazy evaluation in order to do distributed memory parallel computing. Then you run, then you clean up. And after I think the result has been calculated. Yeah. After you've done with this computation, and I print out some check while computing, then you can use some visualizer. No, I shouldn't say visualizer. It's actually a renderer. I do something on the fly, and so that it can be rendered by this application. So you can see your result. And it will output this visualized result on the fly, so you can check the result anytime while you are doing this computation. Oops. Okay, so it's pretty much about it. I'm still working hard with SOLVCON. By the way, I've done this work while I'm studying in Ohio State for my PhD, and I'm still doing that with our research group. We have some other research projects going on for other physics like biomechanics and some hydroacoustic or aeroacoustic things. Because this solver is very good at calculating propagating waves. And I personally is trying to do some electromagnetic calculation. And but this is not my day job. My day job is well, I'm a semiconductor engineer right now, and so it's quite remote to this application. But the technology I've learned has been very promising, and I've applied quite a lot of this capability in my work. So for right now, I'm thinking about how to further simplify this whole structure. So the gray boxes in this diagram is what I think I should avoid in the future. And I'm working on to remove them from SOLVCON because I can replace them. For example, for DMPC, actually I can use MPI for pi. Yeah, from the beginning, several years ago, I think maybe I can come up with a better solution, but it turned out that I can't. So I think I really need to use something more advanced to do something they are really good at. So, and previously I was using C types to do interfacing between Python and C, and it was very convenient. But when the code base grows to a significant size, then it's not very easy to manage all this interfacing and dependency. C-types could be a bad idea about doing this. So I'm converting most of my code from C-types to SOLVCON. So I mean, SOLVCON is better, could be better than C-types for maintainability. Okay, so in conclusion, we have a quite successful story with using Python for high-performance partial differential equation solvers. And we've done multiphysics, and the result is great. You don't really see, I've mentioned about PhyPy and Phoenix. They are both great projects, and but I think in terms of time-accurate solutions, I think we are doing pretty good for HPC and for multiphysics. In general, what you need to do is to replace the solver kernel, and you can have a very fast speed. But you don't see a lot of documentation with SOLVCON because I don't have time to write them. So it's still in a very early stage of development. But the structure and architecture is quite simple and clear, and we stress a lot on parallel computing. So what we hope is if we can get access to a really large machine, we want to tune the code to really do supercomputing. And most important, it's very productive. I think more than 70 or even 80% of codes are written in Python, in SOLVCON. So we still need to do some low-level things. We need to do CUDA. We need to do C. But most of the things are Python. And it really saves a lot of time for research. So, yes, Python rocks. You don't agree with that? Okay. So thank you very much for listening to this talk.
Does anyone have any questions? Any questions? Okay.
Oh, thank you for your presentation. Compared to other open source CFD software, such as, do you know OpenFOAM?
I've been studying with OpenFOAM. OpenFOAM actually is implemented in C++,
yeah.
And it's used in projection method. It's mostly designed for doing low-speed flow. And what I'm doing is for high-speed flow, which means supersonic things. And we have a lot of, we need to the whole point of doing this is to capture shock. Capture this thing. Okay, so for supersonic flow, there's shock waves everywhere. And the reason we call it shock waves is that it is some discontinuity in space. And we have already discretized the spatial domain. So if this discontinuity does not happen right on the place we discretize our space, then it's not really a discretized. It's not discrete, right? Then the discontinuity become continuous. So that's a problem. We need to capture that shock. If we cannot capture shock, the physical phenomena will be totally lost. So for projection method, it's not designed for capturing shock. We cannot use it. But OpenFOAM is a great tool. I think it's currently being supported by CGI and have a lot of commercial support. So you can use that. And they have a decent parallel computing support. Yeah.
Oh, thank you.
Thank you.
Okay, I think we have time for one more question, if anyone else. Okay, so I guess we can close the conference. Thanks.
Thank you
for the presentation.